there, this is Pierre-André Mathieu, and I'm here today with a tutorial on how character repulsion works in a Devil May Cry style character action game. Now, I'm going to play this and show you the results here. As you can see, the player is moving the enemy. Additionally, I can do an enemy step. One of Devil May Cry's hidden features. And this is what I'm going to show you on today's tutorial. In my character blueprint, I'm going to explain to you the 6 macros I use for a function that calculates the repulsion between two characters, the player and the enemy. So the first macro I'm going to explain to you is facing through. This is the internal logic for the first macro. This input here shows the input execution of this macro. When that macro is executed, the flow enters. The branch here is a standard conditional node, as it takes a Boolean input on its condition, like phase through. And it directs the execution flow to either true output of the pin should the phase through Boolean be true, or false if the phase through Boolean is not working. This variable gets the value of the Boolean. It likely exists within the character or component where this macro is being used. Get phase through variable is connected to the condition input of the branch node. The macro has 2 outputs. One is connected to true output of the branch node and is labeled true. The other is connected to false output of the branch and it's labeled as false. The macro is facing through essentially checks the value of a Boolean phase through. Whenever this macro is being used, it retrieves the current value of the phase through variable. If this variable is then used as the condition for the branch node, I'm sorry. What I meant to say is that the value of phase through is used as the condition for the branch node. If the phase through variable is true, then the execution flow exits the macro through the true output pin. However, if it's false, the execution flow exits the macro through the false output pin. What this macro does is it provides a simple and reusable way to check if the character or whatever object this macro belongs to is currently in a facing through state. This state could be used for various gameplay mechanics like ignoring collisions. If phase through is true, the character might be able to set up ignore collisions with certain objects or other characters. Special movement abilities. Phasing could be a temporary ability that allows the character to move through obstacles. Visual effects. This phase through macro might be associated with visual effects such as the lightning, in encapsulating this check in a macro like this. The logic can simply be reused in multiple places within the character blueprint without having to duplicate the get variable and a branch node every time, which improves organization and maintainability. The next macro I'm going to explain is Repel Sphere Loop. The input entry point for the execution flow is when the macro is called. This is a standard loop node in Unreal Engine as it iterates through an array. The input execution pin starts at the loop. The input array in which the loop iterates over is where the input is connected to a node labeled Repel Spheres. This node contains an array output that is indicated by multiple pins icon, as it likely what I'm saying is that it's most likely that this node retrieves or generates an array of sphere related data either through sphere components, actor references, or structures containing sphere information. The loop body execution output that fires for each element in the Repel Spheres array is connected to the loop body output of the macro. This data output provides the current element from the Repel Spheres array within each iteration of the loop, as it is connected to the array element output of the macro. This one I'm not going to worry too much along with this one, because that's not my primary concern. Anyway, this execution and input receives the loop body execution from the for each loop, as it exposes it as an output of the macro. This data input receives the array element data from the for each loop, as it exposes it as an output of the macro. The Repel spheres loop macro takes an execution input and then does the following. It receives an array of spheres. The exact nature of these spheres isn't fully clear, but they are likely represented by some data structure. This array is the output of the Repel spheres node, as it iterates through each element in this Repel spheres array using for each loop. For each sphere within the array, it triggers the loop body output execution pin of the macro as it provides the current sphere's data through the array element output data pin. The purpose of this macro is to perform some action on each sphere in a collection. The name Repel spheres loop states that the action performed within the loop connected to the loop body output will likely involve repelling these spheres in some shape and form. The uses within the loop body are as follows. It calculates a repulsion force based on the sphere's position and the other nearby objects. It applies a force to the sphere's velocity or position, checks for collisions between the sphere and other objects, and updating a visual or physical properties of the sphere. What this macro does, it provides a fresh, encapsulated way to iterate over a set of spheres as it applies a repelling logic to each one. The actual repelling logic will be implemented inside the blueprint nodes connected to the loop body output of this macro. Now let's look at how Repel spheres is used. As you see here, I have a Repel sphere on the character, and I located the parent socket to spine 2. How I add the sphere? I just click on mesh, search for sphere collision like this, and then click on it. Then after I click on it, I rename this variable name from sphere collision to Repel sphere. After that, I set the sphere radius to 50, and I have this. After that, as I said, I have to locate the sphere to spine 2. This right here shows a part of the construction script of the character blueprint. The construction script is like event begin play because it runs every time an instance of the character blueprint is created within the editor or at runtime. This node here you see is setting the value of a variable named Repel spheres. The array icon that indicates that Repel spheres is an array. This node essentially creates an array, as it indicates the first element being added to the array. It's linked to the variable named Repel sphere, the sphere collision I created. The Repel sphere is a variable of a type Repel sphere. It's likely an object reference to a sphere component or an actor containing a sphere. So what I'm getting at here is the construction script is initializing Repel sphere's array, creating an array and adding the value of the Repel sphere variable to it, which means that the character will have a collection of an array of Repel sphere objects associated with it. What I'm showing you at the viewport are the details for a component Repel sphere selected within the character's viewport. I'm not gonna waste my time explaining the whole thing, so I'll just explain what the function does. The Repel sphere's loop and the presence of sphere collision component and the Repel sphere system likely works as follows. Repel sphere's loop macro iterates through the Repel spheres array, which currently contains one Repel sphere component. Inside the loop, the logic will likely use the information from this Repel sphere component, its position and radius, to calculate and apply a repelling force or effect to either objects that enter its collision volume. In that sense, the character has either one or more defined spherical collisions area, represented by the Repel sphere components in the Repel spheres array. The Repel spheres loop macro then represents each of these spheres to implement a repelling behavior on other game elements that interact with them. The fact that Repel sphere is marked as static suggests that the repelling effect is likely based on the character's movement and the fixed position of these spheres relative to the character, rather than the spheres themselves moving independently. The next macro I'm going to explain here is player/enemies loop. This macro here shows how player/enemies loop appears when placed within a certain function, in which I'm going to show you, that being calculate character repulsion. But for now, I'm going to explain to you what this function is. This function indicates the macro's purpose: to loop through either players or enemies. It's where the execution flow enters the macro. The integer input likely determines whether the loop iterates through players or enemies. This output will be triggered for each character, player, or enemy process within the loop. This one right here will provide the current character being possessed within the loop. Now that I explained this, let's explain the internal build for it. This one right here shows the logic inside player's enemies loop macro. This integer input is received from the macro's input pin. This pure function, likely a custom or standard Unreal Engine node, retrieves an array of player characters. This one right here retrieves an array of enemy characters. This node here chooses between two different array outputs based on the value of the character index input. The index right here connects to the character index input of the macro. GetPlayer's pure function is connected to option 0, whereas getEnemy's pure function is connected to option 1 of the select node. This output here is either an array of players or an array of enemies, and it's connected to an array for each loop, which is the standard loop that iterates through the array selected by the select node. The input execution starts the loop. After connected to the return value, the array element basically inherits from the select node of these two pure functions. This execution input receives the loop body execution from the for each loop as it exposes it as an output of the macro, whereas this data input receives the array element data, the current character reference from the for each loop, as it exposes it as an output of the macro. This macro, the player/enemies loop, is made to perform some actions on either players or all enemies within the game. The specific action would be implemented within the character blueprint node connected to the loop body output of this macro. Its uses being 1. Applying a global effect to all players or all enemies. 2. Checking the state of each player or enemy. 3. Sending information to each player or enemy. And 4. Performing calculations based on all players or enemies. The character index input makes this macro very versatile, as it allows the same logic applied to different groups of characters based on a simple integer value. Now let's take a look at these two pure functions individually. This pure function is getPlayer's pure function. The entry point of the function is this, obviously. The pure designation indicates that this function does not have any side effects, as its outputs is solely determined by its inputs, that being the blueprint interface function, in which I will explain in a second or two. This node has a target input connected to getGameMode and a return value output, which is the array icon right there. The target is specified as player game mode blueprint interface, which means that it's calling a function on the game mode. More precisely, this game mode. But I'm going to be focusing on this for now. This function getPlayers returns an array of something, likely a player character reference. This function retrieves an array of player characters by calling upon a function, more precisely this function, on the current game mode, which is expected to implement the player game mode blueprint interface. The function then returns this array. Now that I explain what getPlayer's pure function does, I'll explain to you next what this function does. The entry point works the same as the getPlayer's pure function. And like getPlayer's pure function, it has no side effects. It also has a target input connected to getGameMode and a return value output, which is this array icon right there, is linked to the return node here. The getEnemies pure function returns an array element like the getPlayers, but instead of players, it gets enemy character reference. This function retrieves any array of enemy characters by calling upon it on a current game mode. Like the getPlayers pure function, the getEnemies function returns its array. In a nutshell, both getPlayers and getEnemies functions are designed to retrieve arrays of character references by calling upon these functions on the game mode. The game mode is responsible for managing and providing access to these lists of characters. The pure designation indicates that these functions simply fetch the data without modifying any state. As to where these two come from, well, I'm going to double click to show you where these two functions come from. These two functions come from player game mode blueprint interface. The blueprint interface in which I created in my blueprint interface folder. What I did here is I add these two functions, getPlayers and getEnemies. I rename outputs return values. Of course, you could name them player references and enemy references, but I'm just gonna leave it as return values. By Unreal Engine standards, so to speak. Anyway, when I add a new output argument, it normally shows the red boolean. So I'm just going to search for character blueprint and select object reference. After I do that, I'm going to click on this variable container and change from single to array. I did the same thing with enemies right here. After I'm done, I have to compile and save. Inside this game mode, I have to click class settings and add implemented interfaces, which is the player game mode blueprint interface. I have to click this and search for player game mode blueprint interface. Of course, I've already done that, but that's how I have these interfaces right here. Then, when I double click, I have getPlayers and getEnemies. These two variables both stem from add unique from set characters, and contains from the actor class, which is this, but I'll be going a little more details on that later, but I'm showing you where these variables stem from. Anyway, the enemies stem from add array, which the new item stems from the actor class. What I'm getting at here is that I'm using these variables within the interfaces so that way I can extract the data from the get game mode without casting, because casting affects the frames per second and overall performance within my project. And quite honestly, I learned that from a comment I made in my second tutorial video that evolves around camera auto adjustment and enhanced movement. And I really need to think about how I'm going to approach this without casting. Alright, let's move on to this macro here. Repel spheres loop without facing through macro has a purpose: to loop through the repel spheres while specifically considering a phase through condition. This is where the execution flow enters the macro. This output will be triggered for each element processed within the loop inside the macro. This will provide the current element being processed within the loop. This is the internal logic for it. This entry point for the execution flows when the macro is called upon. Of course, you already know these two and what they do. But what I'm telling you is that this node has an array output indicated by the multiple pins icon. It retrieves or generates an array of sphere-related data through repel spheres, similar to the regular spheres loop macro. The execution output that fires each element within the Repel spheres array is connected to the loop body output of the macro after a branch node, which is the one I have here. This data output provides the current element from the Repel spheres array each iteration of the loop. Well, during each iteration of the loop, but you kinda get the gist of what I'm saying here. Anyway, it's connected to the array element output of the macro. The branch node is, well, as I said, within the facing through macro is a conditional node that controls whether the loop body output of the macro is executed for the current sphere. Well, similar to the face through macro, but different. The condition of this branch is being checked is the result of an AND operation. This checks if the character this blueprint belongs to is equal to the target. The target input is not likely visible, but it's likely connected to the current array element, which suggests it's checking if the current sphere is being considered belongs to this character itself. This node inverts the boolean value of the face through variable. This combines the results of not equal and not face through check. The true output of the branch will only be executed if both of these conditions are true. If the character blueprint itself is not equal to the target sphere owner, meaning the sphere belongs to another actor, then it can fire up. If face through is false, meaning the character is not currently facing through the state, then it can also fire up. This execution input receives the true execution from the branch node, which means the loop body of the macro will only execute for Repel spheres that belong to other actors, as this character is not facing through. This data input receives the array element data, the current sphere reference from the for each loop, as it exposes it as an output of the macro. What this macro does is it iterates through the collection of Repel spheres. However, unlike a simple loop, it includes a condition to filter which spheres are processed within the loop body. The loop body will only be executable for the spheres that 1. Do not belong to the character that is running this macro, and 2. Are encountered whenever the character is not in a facing through state. What this macro does is it's made to apply a repelling effect from external spheres belonging to other actors, whether it be a player character or an enemy character, onto this very blueprint, but only when the character is not in a state where they should ignore such repulsions, especially when not facing through. This could be used for interactions with the enemy projectiles, environmental hazards, or other game elements that have a repelling influence. The facing through state would allow the character to temporarily bypass these repulsions. This macro is a bit complex, so I'll do my best to explain it. This input here is at the very start of this macro. This input right here is a reference to sphere collision object reference. This right here is a reference to scene component object, and this is an element from an array of sphere data, as it is referenced to the sphere collision object. This right here is at the end, as it execute things based on its internal components. The first world location is a vector representing a world location. Second world location is a vector representing another world location. This one here, added float, is a float value. This output right here is another flow representing a distance. Now let's move on to its internal structure. The macro input receives the input values for sphere collision reference, scene reference, sphere array element, and input. This node gets world location of the sphere collision reference input, which means that the location and is likely a sphere collision component. This other node right here gets the world location of the scene reference input, which is likely the location of a scene component or an actor, but in this instance I'm using a scene component, not an actor. This node calculates the vector distance between two world locations obtained in the previous steps. Vector 1 is from the sphere collision reference, whereas vector 2 stems from the scene reference. Get scale of sphere radiance stems from the sphere collision reference. What this does, it gets the scale radius of the sphere collision reference input. This duplicate right here, or copy, stems from sphere array element. It extracts the scale radius of the sphere array element input, which means that the sphere array element is also a sphere collision component, or an actor that has a sphere collision. This minus node subtracts a constant float value from the scaled radius of the sphere collision reference. This one right here subtracts a constant float value from the scale radius based on the sphere array element. The two float clamps results of the subtractions to be within the range of the minimum of 0 and the maximum. I'm sorry. The minimum is 0, whereas the max is the get sphere collision scaled radius. Yeah, the minimum is 0, whereas the max is these two. The plus float node adds the clamp foot values together. Now this is where the subsequent logic and macros output came into play. The less than vector compares the vector distance calculated earlier with a 0 vector. This will be true only if the magnitude of the distance of the vector is less than 0, which is generally never the case for a valid distance. This might be an error or an unusual check for a specific scenario. This uses the Boolean result of the vector less than the comparison of its condition. If that condition is true, it leads to a get world location of the sphere array element. If it's false, it also leads to the get world location of the sphere array element. So what I'm getting at here is that get world location through sphere array element gets the world location of the sphere array element input. The first world location connects the return value of the get world location of the sphere collision reference, whereas the second world location connects the return value of the get world location of the sphere array element. This output right here is linked to the result of the plus float node, the sum of the clamp scale radius. The distance float, on the other hand, is linked to the size magnitude of the distance vector result. The calculate world location and distances takes a sphere collision reference, a scene reference, and another sphere-like element as an input. Then it does 1. Calculates the world locations of the initial sphere collision and the scene reference. 2. Calculates the vector distance between these two locations. 3. Calculates a combined clamp value based on the scale radii of the initial sphere collision and the sphere array element after subtracting 1 from each radius. 4. Compares the vector distance to 0. The purpose of the branch based on the comparison is unclear, but ultimately both paths lead to getting the world location of the sphere array element. And 5. Outputs of world location of the initial sphere collision, the world location of the sphere array element, the combined radius value, and the magnitude of the distance vector between the initial sphere and the scene reference. The entire purpose of this macro is to calculate the spatial relationships and size between different sphere-like objects and a scene component. The output suggests that it might be useful for determining the distance between a sphere and a scene element, combining size information of two spheres, potentially for interaction calculations, and retrieving and passing along the world locations of these elements. The unusual vector less than 0 check suggests that there might be a specific edge case or logic that isn't immediately obvious from these calculations alone. I'll explain to you this very last macro, which is can contain repel actors. This input pin is where the execution flow enters the macro. This input represents the item, actor, or object being checked for the containment within the repel actors array. As for the output execution pin, this one on top will be triggered only if the item to find is found within the repels actor array. Repel actors array. This one, on the other hand, will be triggered if the find item is not found within the repels actor array. Let's take a look at its internal structure. This internal logic is how it's built within this macro. The input receives the execution input as it finds the item to find data. And I'm talking about this input right here. Not this one. This one. This input only deals with the execution from the start, whereas this one receives input execution as it finds item to find data. This node here checks if a specific item is presented within an array, and the array is repel actors array. This icon right here multiplies the boxes, which means it's an array. I know it's very obvious. Connected to the, and this one right here is connected to the item to find input of the macro. This one right here outputs a Boolean variable, true only if the item to find is found in the repel sphere actors array, and false otherwise. This node here is a standard conditional node. It takes the Boolean input on its contain pin and directs the execution flow based on the following result. And it's specifically connected to the Boolean return value of the contains node that holds repel actors. If the contains node returns to true, the execution flow goes to the true output pin of the macro. However, if it's false, then the execution flow goes to the false output pin of the macro. This execution output is connected to the true output of the branch node, whereas the false execution output is connected to the false output of the branch node. Can contain repel actors macro checks if a given item to find is presented inside an array called repel actors. Then it outputs the execution flow through either its true output pin only if the item is found, or its false output pin only when the item is not found. The purpose of this macro is to quickly and easily determine if a actor in particular or an object is considered a repel actor. By checking its presence in the repel actors array, this could be used for various gameplay logic, such as 1. Applying specific repulsion behavior only to certain actors, 2. Preventing certain actors from being repelled, and 3. Identifying which actors should trigger a repelling effect. In encapsulating this array check in a macro, it can be reused throughout the blueprint without needing to duplicate the contains and branch nodes. Now that I explained to you on what those 6 macros do, I'm going to explain to you how calculate character repulsion works. What I did is I add a function, then rename this function calculate character compulsion, which I did right here. It's classified as collision. So yeah. An input type character blueprint is likely the character from who the repulsion is being calculated. The standard exit point after the function has executed. Now, let's move on to its internal structure. This is the starting point of the function's logic. This clears all elements from an array, the repel actors. This clears all elements from repel vectors. This macro is facing through executes a macro that returns true only if the character is currently facing through objects. Otherwise, it's false. And if it is false, then it's using repel spheres loop, which executes a loop for each element in an array repel spheres. The current element output through the array element pin. This node for loop executes a standard for loop with the first index set to 0 and last index set to 1. The current loop index output is through the index pin. Most precisely, player/enemies loop, which executes a loop for each player or enemy character based on the character index input, which is connected to the index from the previous for loop. The current character output is through the array element pin. And what I'm using from the player/enemies loop is repel spheres loop without facing through. A macro that executes a loop for each element inside the repel spheres array, but only if the character is not facing through objects. The current element is output through the array element pin. which uses the 2 pins from calculating world location and distances. This very macro that takes a sphere collision reference, a scene reference, and a sphere array element as input and outputs world locations, and added float and a distance float. As I go further, I'm checking if an actor can contain repel actors. This macro checks if a given item to find connected to the array element from the players/enemies loop is presented in the repel actors array. The outputs are true or false execution pins. If I go even further, I'm adding repel actors and vectors. The branch node inside here executes different paths based on the outputs of the can contain repel actors macro. It's true only if the actor can contain repel actors. If the branch is true, then the array element from players/enemies loop is added to the repel actors array. In finding an element in repel's vectors, okay, hold on. In finding the element within the repel's actors array, I'm attempting to find a specific element inside repel's actors array. When I get elements from repel vector array, I retrieve an element from the repel's vector array at a specific index right here. The vector length calculates the length magnitude of a vector. This node compares two existing float values. This other branch node adds another conditional check based on the comparison result. This node right here sets an element at a specific index within the repel vectors array. Now, If this is false, then what I'm doing is simply normalizing repel actor and vectors. By adding repel actors array, I add an element to the repels actors array. This right here calculates the unit direction vector from a from to a to vector, and it stems from calculate world location and distances. This node here normalizes a 2D vector, which is get unit direction, I'm using this to multiply normalized 2D vector by this node, which minuses the added float and distance float. Actually minuses the distance float to the added float. And when I add to repel vectors array, I am adding an element to the repel vectors array. To put it bluntly, this function is a core part of a system for calculating and applying repulsion forces between the character and other actors based on a spherical collision components. What it does is it clears the repel actors and repel vectors array, determines if the character is currently facing, iterates through the character's own equal repel spheres, iterates through all player and enemy characters. And for each player or enemy, it checks if they can contain repel actors. If a player or an enemy can contain repel actors, they are added to the repel actors array. Additionally, it performs some logic involving the repel vectors array, potentially based on the distance or other factors. It uses a macro to get spatial information and normalize vectors for repulsion calculations. Calculate character repulsion function gathers relevant actors and their sphere components, calculate distances, and prepare data, mostly actors and vectors, for the actual application of the repulsion forces, taking into account whether the character is currently facing the multiple loops, and conditional logic suggests a complex interaction system based on proximity and specific actor properties. Moving on to character repulsion. It works kind of like calculate character repulsion, but different. It's similar in a sense that is classified as collision. This is the start of the function's logic. connected to the target input of the character Repulsion, I have add world offset. This input right here is linked to the output of the get vector array average node, which indicates that the character's world location will be offset by the average vector of an array, but it is divided by a float input by 2. By placing a check mark on a sweep, the movement will perform collision detection and potentially stop if something is hit. And since the teleport is false, the movement will be a physical movement, not instant teleportation. This node right here is connected to Repel vectors, which means that it is indicated by multiple pins and icon signifying an array of vectors. The output of the average determines all of the vectors within the Repel vectors array. The character repulsion function takes a character blueprint as an input and applies to a world offset to its location. Then determine the average of vectors stored within Repel vectors array. This movement is performed with collision detection enabled. This function is designed to move the character away from other objects or locations based on a collection of repulsion vectors. The Repel vectors array would presumably be populated by other parts of the character's logic, as seen in the analysis of the calculate character repulsion function, as it is based on detected nearby objects or forces. In taking the average of these vectors, the character will move in a direction that is the average of all the calculated repulsions. The sweeping motion ensures that the movement respects collisions inside the environment. Alright, now I'm moving on to the section of the event graph for the game mode, which is the third-person game mode, and I'm going to break down on what's happening here. The event tick fires every frame, meaning the logic connected to it will execute endlessly. And from here, I have 2 for loops. These 2 are running in parallel. as they are set to iterate from a first index of a 0 to a last index of 1, meaning each loop will execute twice, with the index output being 0 and then 1. These two select nodes have an array input labeled players connected to option 0, suggesting that players is an array containing player character reference. Both select nodes have an array input named enemies connected to option 1, suggesting that enemies is an array containing enemy character references. Based on the index from the for each loop, each select node will output either an element from the player's array if the index is 0, or an element from the enemy's array only if the index is 1. And from there, I have two character repulsions, the calculate character repulsion and character repulsion. The return value from each select node is connected to a target input of a calculate character repulsion function call, as the function I stated previously calculates and adds repulsion force to the targeted character. So the game mode on every tick in a nutshell, the game mode on every tick iterates through the first two elements of both the players and enemies arrays. For each of these characters, it calls upon character calculate repulsion function, triggering the repulsion logic on them, suggesting that the game mode is actively managing the character repulsion system by regularly telling the specific player and enemy characters to calculate their repulsion forces. The reason for this lies on iterating through these first two elements of each array based on the for loop limits. Isn't explicitly clear from this zoom out view, but amplifies only that a subset of players and enemies have their repulsion calculated each frame by the game mode. To give it a test, I'm going to add a breakpoint. When I play it, it automatically fires it. Hold on. Yeah. So I'm gonna remove that. I'll add 2 breaking points. It does the same. So I'm gonna have to test it out and see if it works. As you can see here, the enemy is repulsed by the player's movement. But how does this stuff works? Okay. The event begin play is where the game mode initializes everything I have here. Connected to the set characters, I'm using it as an alternative to casting, a blueprint interface, so to speak. It stems from the character blueprint interface in which I made in my blueprint interface folder. The character blueprint uses this. From the return value, I'm using this to add uniqueness to the existing array of players. After that, I use this to determine whether or not the game mode is using isPlayer from set characters. If I go to player character blueprint and search for isPlayer, I place a check mark on that to determine if it's true. But if I uncheck it, the player is facing through the enemy. And that's a problem. But not to worry. If I place a check mark on that, the enemy is repulsed by it. If it's true, then the initialization is using this, which loads a subclass reference and returns class of the correct type only if the load is successful. And the type I'm using here is character blueprint class. The asset class I'm using is basically character blueprint. I can just drag it and add it there, but as a stop. So I have to manually search and click it. And once I do, I extract a node from here and cast to character blueprint class. It was once an impure class, but I converted it to pure class. Now, from as character blueprint, I extract a node and click is valid class. What this node does is it determines whether or not I'm using the cast2 character blueprint class, and its input is in reference to object class reference. From the return value, I'm using this to ensure that this and the success boolean from the cast2 character blueprint class is equal to one another. From there, I'm using branch to determine if it's true. If it is true, then I'm getting the actor of class based on the character blueprint class. When I return the value, I'm containing the player characters, except I'm not containing the player characters and determining whether or not this along with this is valid. And if it's true, if I'm not containing the player characters while acknowledging the fact that if it is valid, then what I'm doing is adding an array of enemies to fight. I always wondered if I can do it without this. Well, as I make changes, you probably not gonna like what I'm about to show you. That being the results. When I approach the enemy, I'm facing through, which can only mean that what I'm doing here is not working. I'm facing through the enemy. The enemy isn't repulsed by my movements. But when I put it back to the way it was before, the enemy is repulsed by my movements again, as it is. So basically, that's all there is to the character repulsion system. If you enjoyed this video, please like and subscribe to my channel for future tutorials such as this, and keep in mind that what you take and learn from me is yours to do with as you see fit. Peace out and enjoy the rest of your day.